Hello, my name is Angelina Altschuler, and I am a Siebel Scholar from the class of 2013.
My name is Atharva Gore, and I'm a Siebel Scholar.
I'm Anshan Peck, and I'm a Siebel Scholar.
Hi, I'm Helen Saad, and I'm a Siebel Scholar.
My name is Ameya Fudke, and I am a Siebel Scholar from the class of 2013.
My research focuses on studying mechanisms in early organ failure when a patient goes into shock. So when someone goes into shock, this is when they lose either a lot of blood from an accident or their blood pressure is having trouble being maintained at the normal level. So we study what organs fail first during this process and ways to intervene to prevent further dysfunction in the animal or the human. And eventually this will hopefully lead to ways to treat organ failure and prevent the cascade that we traditionally see in the clinic.
My research focuses on induced pluripotent stem cells. Now, induced pluripotent stem cells are they recently won the Nobel Prize. The professor who developed them did, at least, Shinya Yamanaka. And they're this revolutionary discovery that's going to completely change medicine and the way we do clinical trials for drugs and any sort of preclinical testing as well. Induced pluripotent stem cells are a technology where you can take a piece of a patient's skin, literally just a little skin biopsy, just a couple millimeters across, take that piece out, take it into a lab, and treat it with these factors that convert it back into a embryonic stem cell-like state. And then these embryonic stem cell-like cells can then be turned into any cell type in the body. That's what makes embryonic stem cells so interesting, is that you can basically turn them into anything you want. So now we can take a piece of an adult's skin and turn that into, say, a kidney or a liver for that person. You could even, the technology is still being developed, of course, but that's the hypothetical goal of this technology. You could literally just take a piece of a person's skin and grow them their own kidney to put back into their body, which would fix a lot of the problems of transplant rejection potentially and graft versus host disease, etc.
So my research is about the motion of microorganisms, which is like bacteria or sperms. So because of their small sizes, it is very hard for them to swim. The situation is actually like putting us humans, like you and me, into a pool of very viscous honey. So you can imagine that it is so hard to swim in that scenario. So all your freestyle swimming, your flapping motion will not work at all. But microorganisms have to swim. Like bacteria, they have to move to find food. And sperms have to swim through a long journey to reach the egg to make a reproduction happen. So how do they do that? So it turns out that nature has developed very interesting strategies for these microorganisms to swim. So part of my research is to use mathematics and physics to figure out the secrets of these microorganisms swimming, and then to provide a better explanation of their motion, and then to better explain and actually predict their motion. And then this will better explain many interesting biological phenomena associated with their motions.
The smell of a flower, the memory of a walk in the garden, my discussion with you, all of these experiences are made possible by our brain. So my main focus is to understand the brain, which is the siege of intelligence, and use theory and mathematics guided by experimental findings to build a virtual model that can help us understand the levels of details that are needed in order to build an intelligent system. This will help us engineer a brain and consequently engineer better health.
My research deals with developing synthetic materials that are inspired by nature. So we look at how nature has designed several materials, and then we see if we can take some clues from that and use that to design synthetic materials that capture those properties. So the specific materials that I focus on are materials to stimulate bone regeneration, and we do that by copying the structure of bone, as well as materials that can heal themselves, and we do that actually by literally mimicking Velcro on a molecular level.
So growing up, both my parents were scientists, and I always participated in science festivals. So I remember doing a science project in about 4th grade, and our question was measuring the heart rates of animals that were our pets basically. So we went around and measuring with a stethoscope the heart rates of these pets and these cats and dogs and making these correlations. And then I decided from then that, I really liked biology and math and the interaction between the two. So, going through and growing up, I chose bioengineering and I came to UCSD because of the bioengineering program. So, and I've been here ever since.
I was motivated to do my research in this area by a lot of different things, but it really started early in life. I'm very lucky to have had parents and teachers who fostered my interests and allowed me to sort of explore science as a whole. One particular memory that came to mind was when I was in 6th grade, my teacher actually had the whole class participate in a thought experiment. And he pretended to be an alien, basically, and said, okay, I don't believe in air. I don't believe in gas. Convince me that this exists. And I mean, that seems simple. You'd say, oh, well, you can feel the wind rushing past you when you run. And he would have an explanation for that wasn't based around air or gas. And so we as a class had to come up with whatever evidence we could without using any tools. Like he said, no technology allowed to make him come up with gas as existing. And he sort of used this as an analogy into both atomic theory and biology and sort of the founding concepts of, well, we can't see cells physically without tools, but this theory's been around for long before that. How did people come up with it? That combined with just in high school, I had teachers that were very interested in using computers and sort of the more old school science together. So we actually were exposed to computational biology at a very young age. And this led me to want to pursue research in bioengineering.
It is actually a sad story. So I was a mechanical engineering student, and I wasn't interested in biology at all. But when I was in college, my younger brother got a terminal stage cancer, and unfortunately he passed away. So at that point, I decided that I want to do something about life science. I want to contribute my engineering knowledge to see if it can be used to save other people's life. So that's why I want to do something about biology, and because I like fluid mechanics as well, and that's why I come to work with Professor Eric Loga and in biological fluid mechanics at UCSD.
I was always fascinated by the brain, and I was born in Lebanon. There was no program that helped me study the brain, so I decided to study computer engineering. And then I worked for 5 years in the same field, but I always had this idea, like, what's the brain? Why are we more intelligent than all the systems around? What makes us this much powerful in terms of thinking, behavior? And this idea was haunting me, and I had it like a dream that I wanted to make real. So I decided to come to the United States and join the UCSD program in bioengineering, where I'm focusing on studying the brain.
So I have some personal motivations as well. I've seen a lot of relatives have bone fractures, and the grafting procedures that I know of in bone are extremely painful. And so that's really what stimulated my initial interest sort of in studying synthetic materials in bone. And then as I got more and more into the field, I started to understand how fascinating, bone is as a tissue, and how fascinating synthetic materials are just because of all the cool things you can do with them by changing their structure around.
So I study shock, and shock is a pretty interesting problem because there's really no preventative way to deal with it. People just cope with it, and they basically just try to keep people alive, not really reverse the shock. And so our research is really looking at reducing patient suffering in hospitals and people who enter the hospital from traumatic accidents. Trauma in general can happen from any consequence. Like, it could happen to anyone at any time. So it's something unexpected, and I think being able to cope with something unexpected well and revive patients is very important in the future. So I think there are many opportunities for translational approaches to improve the quality of patient life if they are unfortunate and undergo one of these incidences.
The biggest impact of my research will most likely be if induced pluripotent stem cells can make it to the clinic, though that's debatable because there are a lot of problems still, but to potentially lead to safe therapies that people can use to cure a lot of diseases that right now leave people on transplant waiting lists for 5 years, for 10 years even, where people are just on dialysis for a very long time. These people's quality of life right now is not very good. They have to go through all these procedures to stay alive. And right now, even after they get a transplant, if they get a transplant, they still need to be monitored constantly and be on immunosuppressants and be constantly watched to make sure that their body doesn't reject it. With this technology, we have the potential to fix these problems, and organ failure might not be such a fatal thing anymore. We might be able to grow new organs for people. And even if we can't, even if the technology doesn't have the potential, that was so exciting to me. And I really think that this technology can get somewhere towards helping people solve these diseases that just right now don't have any other solution.
So the first impact will be on the science perspective. So it will be an improved understanding of the world of microorganisms, which is everywhere around us and actually inside us. So this is the impact on the science side. And the second impact is about engineering. So imagine if we have our own artificial microswimmers that is as small as these microorganisms, and we can have them travel around our body to fight against the bacteria and to perform surgeries. That would be very great, right? So, but one fundamental question is, how should they move? As I explained, that was very difficult. It is very difficult for them to move when they're such a small scale. And one solution is to look at nature to see how microorganisms, these natural microswimmers do, and then learn from it. So we have collaborated with Department of Nanoengineering at UCSD to design microswimmers that are as small as this bacteria, and then we can load them with cancer drugs, and then we direct this cancer combat drug directly to these cancers, and then unload these cancer drugs to kill the cancers. So this selectively kills the bad cells, which will bring great impact on new cancer therapies, because conventional therapies kill both good and bad cells, like chemical and radiotherapies. So I expect that this will bring a new insight on the treatment of many diseases.
We cannot solve a problem if we don't understand, if we don't understand it well, and we cannot fix a system if we don't know how it operates. And this is what I'm trying to do. We're trying to understand how the brain works in health, how it fails in disease, and how we can fix it. So it's mainly, this research will not only give us insights on intelligence and this powerful network that's the brain, but it will also, and more important, it will also help us devise solutions for medical problems, for people for the blind to see, for the crippled to walk, for victims of dementia to remember.
Well, so the impact that I hope that my research has is developing synthetic materials that can substitute for bone. So this would basically mean that you don't need to take bone grafts a lot of times, which is more painful than the actual surgery, as well as hopefully stimulating interest in science in younger students. I've tried to do that over the course of my graduate work, really try and get the community involved by doing outreach in high schools. And that's really where I hope to make an impact, is stimulating an interest in this kind of stuff in the next upcoming generation of young scientists.
Being a Siebel Scholar is a tremendous honor, and having gone to the conference in Berkeley just this past month, it was really eye-opening. The network of Siebel Scholars is probably what it really means to be a Siebel Scholar, being able to communicate and know that you can always find someone within the community.
Being a Siebel Scholar to me is a wonderful opportunity, and it is fantastic to just have a community of my peers and those from the previous generation and those from future generations that are really the brightest minds from many different fields. And I love the fact that all of this brain power is being put together to work on some of the toughest problems facing humanity. That to me is just wonderful.
Oh, it is such an honor to be a Siebel Scholar and to be in the Siebel Scholar community, which is full of the most talented students in the world. And but to me, what it makes really prestigious is that this Siebel Scholar community cares about the world. He cares about the world, what problem is the world facing now. And so it cares about the society and what we can do about it.
Being a Siebel scholar is a great honor for me. I compare myself to the neuron of the brain, which is the main cell type of the brain. And the neuron becomes more powerful and better fulfills its function the more connected it is. So the more it branches new connections to neighboring neurons, and the more it builds partnerships, let's say, the more the brain is powerful. And being in the Siebel community is allowing me to build this great network of friendship and partnerships whereby I can better serve my society, and I will be more connected and more powerful, let's say, in terms of being able to reach my goal, which is better understanding the brain, helping engineer better health, and also, and very important to me, is to create this network of partnerships and collaborations between people of the world. So my goal is to also start a research center in Lebanon with the collaboration of institutes such as UCSD in the United States, and create this mutual respect and mutual understanding that will help us build a better world and improve building the peace process between nations.
What it means for me to be a Siebel scholar, I think it's being part of a community of people that are not only immensely talented, but want to use those talents towards the greater good. I saw that firsthand at the Siebel Scholars Conference, where every person I met was insanely smart. And yet, every single one had a passion to do something with that intelligence, other than just getting the next great job or, advancing in their career. I mean, the number of initiatives regarding doing stuff outside one's personal benefit at the Siebel Scholars Conference was just outstanding.
I would especially like to thank Tom and Stacy Siebel for making this opportunity possible. Without their vision, the Siebel Scholars Foundation wouldn't exist, and who knows, potentially great things can come out of the organization in the future.
I'm really thankful to Tom Siebel and for this opportunity, and to the foundation as well.
So I would like to thank Mr. Siebel for this great vision of forming this community, of bringing together all the talented people, future leaders in business and technology, to come together to do something to make the world a better place.
I'm highly grateful to Mr. Thomas Siebel for starting such a great program, and I hope that it will continue over years and we have more and more. We build this great network of Siebel scholars worldwide.
I would also really like to take this chance to thank Tom Siebel and the Siebel Foundation for setting up this fantastic program. I'm only a few months in, and I'm already seeing what kind of an impact it can make, not only on my life, but also the kind of impact that it can allow me to make on other people's lives.